students, welcome to the contribution lecture to superconductivity for engineers. The content of this lecture is about novel magnet concepts, thermal equivalent circuits, and cold heads. And to focus on the lecture, I will switch off my video so that you can follow the slides directly. Just a second. Okay, great. Then we might start directly. So what is to be expected from today's lecture? So first, let's take a look at the content. We will for an introduction, look at the selected basics on magnets. Then we will discuss a bit the general challenges which are related to the magnet technology. Then discuss the novel approaches which are hot topics today in magnet technology and in winding wires in the shape of coils, especially high temperature superconducting wires. Then we will take a look at cold heads and the thermal equivalent circuit. And finally, we will go for the learning objectives and close this lecture. Hopefully my pen is working, so I can lead you through the lecture. So let's start with the selected basics on magnets. This is the first slide on that. This is a quite old topic because the very first magnet of this kind was already introduced at the end of the 19th century. And the basics of the magnetostatics have already well known. So diamagnetism, ferromagnetism, is especially that, for example, iron can be used to guide magnetic flux up to a magnetic flux density of 1.6 Tesla, and then saturate it. And here you see the very first apparatus of Faraday. And he already knew that one can use iron to guide the flux and having only two coils in there. So we will do no deep dive into magnet design, but at least one or two things general common to magnets and magnet technology we should mention and note. And especially two tools for the design of magnets are important. And you can guess out of these tools what I always call the magic triple. And this is kind of a gift, and you can surprise people when using this tool, how fast you can give a first sketch of magnets. So the two tools you can use as a back of an envelope calculation is first Ampere's law. This is maybe used for the stationary conditions. And if we apply that to a simple wire carrying a current here in this direction, a current of 1 amp, then at a typical distance of roughly 0.2 millimeter, this corresponds to an integration path here, to a typical length of 1.26 millimeters. Then, according to the equation, to Ampere's law, we will end up with 1 millitesla. And this directly leads us to the magic triple. So this can be, as it's more or less a superposition, it can be used as a superposition principle. If you have 1 amp and a typical length of 1.25 millimeters, then you will get 1 millitesla. If you want to achieve 1 Tesla, then you have to use for the same dimension 1000 amp. If you want to increase the typical length scale by a factor of 10, then you will not get 1 millitesla, but only 0.1 millitesla. So this is the scaling, and having these three numbers on the top of your head, you can easily do a very first sketch of the amperage needed to produce magnetic fields. And the second tool which we might use is the law of Biot-Savart. This means that each and every length segment of a current trajectory will produce a magnetic field. And in principle, you see from this term here that this is proportional to the reciprocal square of the distance to the current trajectory segment. So this can easily be used for that. And just to give you an illustration for that, I have prepared the short calculation of the magnetic field of a circular loop. And you see that here. So again, we have in equation 1, we have the Biot-Savart law. And when we simplify that just along the z-axis, then the equation simplifies a lot. And using the symmetry in this plot, we can get rid of the vector presentation of that. Then we might replace the cosine theta by these equations there. And the integration along the perimeter of the circular loop will then lead to the final result, which is given here. Or if you go for the far field approximation, you see that the magnetic field is proportional to current times cross-section divided by the third power of the distance. And this is a general rule. So this means in far field approximation, each and every magnetic field of a source is decaying with the third power of the radius, and this has to be multiplied with the magnetic moment current times cross-section. You can use detailed FEM calculations for that, but in principle, it's always based on this Biot-Savart if you are not directly in the neighborhood of your current segment. You can use Ampere's law for solenoids too. This is so simple that I do not want to go into details. Just for completeness, this is mentioned here, and you will end up with a general equation for a solenoid here for the expression of the magnetic field. But I just want to bring to your attention that this equation is not always required to be calculated. You can simply think how is each quantity contributing to the generation of the magnetic field, and then you simply have to add this factor in front of that, this mu0, just to get the units right. A solenoid is not the only way to produce magnetic fields. It's perhaps best known from education by school, but there are several other topologies or typical windings to do that. And here is a sketch of or a collection of different windings which are established or which are quite recent. So, for example, the 32 Tesla magnet here, this is a magnet produced by, built by the National High Magnetic Field Laboratory in the US, and it consists of a stack of flat superconducting pancake coils. So exactly the circular loop we have calculated, but now with a lot of turns and stacked on top of each other. The second one, the transformer here, for example, is an example of superconducting Röbel cables, which are wound into solenoids to reduce the AC loss in there. Then for magnets which need really a high number of turns, you will switch to a layer winding, so several turns of the wire on top of each other. Or you might use for rotating machines here, for example, you might use a slightly changed geometry of the coils to create a shape which is suitable for a rotating machine. And if you want to have only a very tiny aperture in your coil, and this is smaller than the critical bending radius of your wires, then you can go to some helical windings so that you can build much larger radius of the individual winding and turn than the aperture itself. And finally, we have this here, which is the robotic winding, which is available in our labs at KIT ETAP. So now we have seen what the general shapes or technology bricks for the windings are, which are more or less well established, but there are some general challenges in magnets. And especially if you look at magnets here, just an example of this picture is the fields, the Lorentz forces which are working outside, and some clamping forces or magnetic fields which are working at the ends of the coils itself. So forces seem to be quite critical. And this comes clear when we look at the next slide here. What we really would like to have in our magnet is, this is the purpose of a magnet, is magnetic field B. But we have already seen for a solenoid, this is a governing equation. And what you can do is that you rewrite the well-known equation here to the left by a special quantity or product which is the current density times the radius, JR. And the advantage of writing that in this way is that you can use that for the other estimations too. For example, the loss, which is associated to at least normal conducting magnets, you can calculate with the same parameter here, this JR squared in this case. Or even the hoop stress, so the mechanical load on the magnet, can be calculated by that. And you see this is going with a second with an exponent of 2 again. And this means the quantity which you would like to have, the magnetic field, is increasing only linear with this factor JR, whereas the loss Q dot as well as the stress sigma is increasing with the second power of that. And this is really what not convenient for a magnet builder. So the problem is, for example, if you remember the critical stress value for example, for steel, this is around 600 megapascal. And 600 megapascal then corresponds to this point here. Or if you look in the graphs on top, this means we would then have already 30 megawatts of loss in a copper magnet. Or if you go even higher to see what we can get out of the magnetic field, this is roughly 25 Tesla. So this means a 25 Tesla magnet is already at the limit what the magnet can really withstand in terms of mechanical load, stress. It's really at the limit in terms of the loss, 30 megawatt for 25 Tesla. This is quite a lot. And this is really the challenge in magnets. In this case, it's the stress is common to all magnets, superconducting or normal conducting, whereas this power ratio here was calculated just for the copper. These electromagnetic forces can be seen as a pressure in the magnet itself. And we take here the example of a 50 Tesla magnet. And if you then divide the energy, create the energy density of the magnet, then you see that it's quite a known formula of that. And this means that this energy density corresponds to 1000 megapascal. And this is already well beyond what conventional materials or conventional steel can withstand. So this is really the limit of magnets in this case. So as we know, we have to face this problem of especially the Lorentz forces working into the radial direction. What is the best approach in normal conducting magnets to handle these high forces in a magnet? And there is a solution which is named after the corresponding inventor, and these are the bitter magnets. This is named according to Sir Francis Bitter, beginning of 20th century. And what he did is he didn't wind wire in coils. He simply stacked conductor discs on top of each other. But he used copper plates, and to control the current path, he added some insulating segments in between, so that finally the current followed this red path here, which is indicated here, to really transport and create high magnetic fields. And you see there are some additional holes in all these plates just to handle the forces in axial direction with some bolts, and to feed the magnet with cooling water. We just calculated that there is a lot of thermal loss, a lot of heat produced by normal conducting magnets, and so you have to add a lot of cooling water into that. And it revealed that it's better not to use pure copper as a material for the magnet, but the best choice would be copper silver. Unfortunately, the electrical resistivity is a little bit increased compared to copper, but on the other hand, you get nearly a factor of 3 in mechanical strength, in tensile strength in this case. And as in these magnets, the forces are mostly working in the radial direction, this is the best choice to realize with bitter magnets. So this was theory. These bitter magnets have been made already in reality. And here we see a typical bitter magnet with, as I already mentioned, with a number of bolts here on the top, and the plates and how they are really designed. This is quite an exercise for experts to design the right geometry with the right positions of the holes in these plates, that you can get a successful bitter magnet. But we have really to take care of the loss and of the power required for such a magnet, and this is shown here. The biggest problem is that you have the relation that the magnetic field is only increasing with the square root of the power you invest in the magnet. And this is again from our expression we saw before. And what you can keep on the top of your head is that the bitter magnets compensate with power and correspondingly with a lot of heat loss to achieve high magnetic fields. And what this really means, you can see on the next slide, because it's not only that you need a big electric supply for such bitter magnets. In this case, it's the range we just calculated before, 24 megawatts and 31 kiloamps for such a bitter magnet. And you will need a specially conditioned cooling water to allow this high currents in a normal conductor and to get the heat away. And you see the installations are really large, which are required for that. And this really led a lot of people to the superconducting magnets, because if you really compare, for example, a 20 Tesla bitter magnet, in this case in the Netherlands, to a 20 Tesla low temperature superconducting magnet, one of these we have at our institute, you see that you need electric power for this conventional normal conducting bitter magnets of 6 megawatts, whereas for the superconducting magnets, it's less than 6 kilowatts. So this is really a difference in operational costs, and therefore it's nice to have the option to build magnets with superconductors. In this case, this magnet here was a layered magnet and not a bitter magnet. So this is quite different. But we will come to that later on. Because even for the layered magnets, there have been popping up new technologies for superconductors, and especially for high temperature superconductors. And in short, these are called Ni coils. And so we are now entering the field of non-insulated coils here. And to make clear what this really means is this slide here showing that for a insulated coil, we might have fully insulated turns, like in this left example here. The red line indicates the insulation around each turn. This means each turn is electrically 100% separated from the others. Or another approach is to have only insulated layers. So this means the very first layer wires are in contact with each other. These are two methods, but nobody thought to really omit all the insulation. But this can be done with high temperature superconductors, and in principle only with these superconductors, with high temperature superconductors. If you are more interested in details, you should attend the summer term's introduction to superconducting magnet technology. But at least this is a new trend in there. And this means there is really no insulation in the whole binding package. This means that all the wires might share the normal conducting cross-section in the total coil. So the stabilizer and copper is shared. And another aspect is that in principle there is some electrical conductivity now, not only in the wire itself, but there might be some current flowing in this direction here, or in this direction. And this is a new feature in there. There is a disadvantage that when it's crossing the copper, the stabilizer, then it will produce some ohmic heat. So there will be some loss associated with that. But as long as your cooling is adopted to that, then this is not really a problem. But a more exciting thing is that the coils are now behaving not as you know that, or with a fixed resistance and a fixed inductance, but in principle now they are kind of transient. We will see that later on. But the initial idea for this non-insulated windings came really to the team who invented that, because in early days there have been some defects in these high temperature superconducting tapes. And the idea was that if there is a defect popping up, then you might simply have the current taking a deviation, and this might not disturb the overall approach of that. And this was not only done by one group in Tallahassee, but we tried to do that in our labs too. And the original approach was binding tape on tape, so metal on metal. What we have introduced in our lab is a little bit different. So you see that here, an example here. This is a typical, this is our first coil for some experiments on that, and we call that an NIVPI 2G HTS coil. So this is the second generation of high temperature superconducting tape, wound with several turns, and it's an NI approach, so there is no insulation in between the turns. So we wound tape on tape, and then we did a vacuum pressure impregnation with some epoxy. So now we have still turns touching turns, but this, let's say, contact resistance is fixed by some amount of epoxy, which makes the whole winding into a robust object. And if you look at the behavior of such a coil, you have to consider the thermal equivalent circuit, which is shown here to the left. So we have a voltage supply, we have some current from the supply. There is a shunt resistance for that to measure the current, and then we have some contacts to the coils, which then lead to some resistance in the overall circuit. And the green rectangle shows in principle the behavior of the coil itself. So we will have some radial current flowing in this direction here. And we will have some azimuthal current, which is flowing in this direction here. And then we will have, unfortunately, these currents and resistances might depend on time. We will see that in a second. And yeah, and even the inductance is not fixed by the geometry of the coil, but depends on the actual current path in there. But what is the advantage of such a complex coil if it behaves so different compared to what we had before? So the main reason to use this type of coils is they are extremely stable. For example, this is exactly the coil you just saw in the picture. And you should know that usually you have a voltage or electric field criterion for determining IC. And what we did is we ramped the current in this case not to IC but to 166% of IC. So this is the level of IC. And we ramped the current over time to this level here. And what happened with the coil itself? The voltage over the coil was developing like that, so far exceeding the criterion for the critical current, but then settling in here at this high level. So it was high, but it was stable and did not quench, and this is due to the resistive contribution by this radial currents. And you see what happens to the Hall voltage we measured at the same time. In principle, you see that it went up to a certain value and then stayed constant. So this means, yes, we produced a little bit more magnetic field out of these coil than expected, but the magnet constant is not a constant for this coil anymore. So current and magnetic field are not 100% proportional to each other in this type of a coil. But you can still achieve this high value of magnetic field in here. So what is the takeaway for these coils? These magnets using these Ni windings are extremely stable and can be operated even in emergency cases beyond the critical current. How about the dynamic behavior of these coils? This was just the stability aspect, and I said that the transient behavior is a little bit different. And this you see here on this slide. What we in principle did is, I will introduce that here. We had a current. Let me put that here, which was over time was increased steadily until this point. Then it was kept stable, and then it was decreased again. So this was the current. Oh, sorry, it vanished, unfortunately. Up to this point and that again. So what you can see is that during the initial ramping period, which is this one here, up to this point, the voltage over the coil was increasing steeply, but the magnetic field was following a little bit, here represented by the voltage by the Hall probe, was not as fast. It took a lot of time until it reached the final value. So the magnetic field rises slowly. The coil voltage was quite steep, and the magnet field was slowly. And during the dwell time, so this would be then this period here. So first, this is the dwell time. Then we have an exponential decay of the coil voltage, which is this seen here, and at the same time an increase of the magnetic field to the maximum value. And for the discharging process, then in the very last section here, this is symmetric to the behavior before. And this really is following the fact that we have a redistribution of the radial current and the azimuthal current in a coil by this changing resistances and the inductance. The inductance is determined not by the geometry of the windings, but by the geometry of the actual current path. And this leads to a non-constant magnet constant in these transient processes. So there's not a mandatory proportionality between current and magnetic field. This sounds to be very complicated, but it really leads to new features and new challenges in these coils, Ni coils, and new options. And I formulated that a little bit sloppy. These Ni coils, they turn a bug into a feature because you can use that. For example, for stable quench in coils in terms of in case of a quench. And this is not only coils which have been built by that, but they have been already quite small magnets built out of that. For example, this is a so-called little big coil insert for Tallahassee, the National High Magnetic Field Lab in USA. But you have to consider that in principle, this coil is not usable. It's so small, little big coil, that it's just, let's say, a hero magnet, one of its kind, and you cannot use this small bore of less than 14 millimeters for something useful except measuring the magnetic field in here. But anyway, this little big coil reached a magnetic field of more than 55 Tesla here. This was the maximum. And this was inserted in a outer magnetic field of 31 Tesla. So this was the extremely high magnetic field assembly. One special advantage of these Ni coils is that you can achieve extremely high winding current densities. So in the coil package, there is a really high current density. And what we already discussed, these Ni coils are really safe with respect to quenches. But they have some disadvantages because they might show some shielding currents. So these tapes here at the rim, they might show some circular screening currents, and which then might lead to extreme forces to the outside at some points, and therefore destroy the coil. And this has already been observed. And the second point is there is this time constant for the redistribution of the current. So you see here is a timeline of seconds, and it's in the range of, let's say, 1,000 to 3,000 seconds until a stable situation is reached. I said this is a hero magnet, but there have been other activities in the field. So, for example, we can look at these at other magnets. So this is again the little big coil. Then there is a magnet manufactured by HTS manufacturer itself, Sunam, of 9.4 Tesla and of 26 Tesla. I do not want to go into all of the details in here, but what is really important is the time constant of everything. So the little big coil, for example, had a time constant in the range of 10 seconds. Whereas these full magnets, they have time constants of 46 seconds, or even here more than 10 minutes for the 26 Tesla magnet from Sunam. And we can easily look at some more details, the technical ramping procedures of the last magnet, this 26 Tesla magnet. The important thing is this is a fully Ni magnet. So all coils are by this non-insulated technology. It's all 2G HTS, so no background field, just all HTS material in there. And the picture shows how this looks like. And now we have a time scale which is not in seconds, but in hours nowadays. And here we see that the inner bore of the magnet is more suitable for users or for experiments. So this is more realistic in there. But you see, this Ni technology is a quite successful approach to create fully HTS magnets of high field. And we will come back to the Ni coils later on in the course of this lecture. But a second approach, which is really new to the magnet or winding technology, is the so-called Duda approach. This was invented in our institute, and this is the very first example magnet out of this Duda, and this is a dimension, you might guess, that of about 40 millimeters. And what is the idea behind? In principle, it's creating a bitter magnet out of the layered structure of the second generation of HTS. So what we did is we had the first idea to follow up on that in 2020. Then this was the first, let's say, desktop model which really has shown that it's possible to create this and having a continuous current path even when not working with homogeneous copper disks as for the bitter magnets, but with this layered structure of the second generation of high temperature superconductors. And how to do that really with this HTS material, with this layered material? The secret is that you have these disks and you have a slit like in the conventional bitter magnets too. And the red part here is the HTS. And we have two types of these elements we have to stack on top of each other. We have a disk up type and a disk down type. So here for the left, disk up type, you can see the superconductor, and here for the disk down type, the superconductor, the HTS, is on the bottom. So I perhaps should not, I should mention that like that. So, and then we had, as you have seen in the picture, we have a copper electrode here. And we have for contacts some indium. The yellow thing here is indium, just to create a good contact to the current feed termination. And then we have to stack the disks on top of each other. So we start with the very first disk. This is a disk down assembly. You see not the red HTS on this left side here, disk down. And then you simply put the disk up disk on top of that. And now we have to assure that the current is flowing from the lower disk to the disk number 2. And this we do in such a way that we slide this area here under the already stacked disk in there. And this is shown here in this sketch. And so we have an electrical contact in there. And this can be done several times. And what we did is this is not an Ni coil. The very first Duda was not an Ni coil. We had a Kapton disk in just to insulate the windings from each other. And to assure a good contact for all these segments, we had an indium wedge, which then allowed a good contact in between these HTS layers. And so the stack is built up, and you have always to slide one disk below the other one, and then you get finally an approach like that. And we used 42 disks in total to go ahead with that. One of the special things with such a Duda magnet is that the current flow is usually flowing in these indium paths up and down in an alternating way. So assume that the current is coming here in this HTS layer, then it's transferred to the next one, going step up, and then coming here, so going there, and then coming, sorry, it's coming here again, and then it has to come down. So this is wrong. Sorry, this is the other direction. So here the current is going up, and here the current is going down through the indium layer. But this is not really an issue. And this is not just a Gedankenexperiment. This has been realized. And here you see how these disks have been looking alike, and the final magnet, Duda magnet itself. There are not only pros for these Duda magnets, but there are cons too. So the challenges are we need really large area 2G HTS. So the availability of the material is important. Then we have the resistive contacts, which should have a low resistivity, not to disturb our superconductors too much. And we have some radial current distribution. I cannot go into details here. If you like to hear more details, as I said, next summer term, superconducting magnet technology. The lecture is discussing that. There are some pros in that. You can really build very small modules out of that. This smaller than you can wind any wire or tape. You can create arbitrary shapes of that, not necessarily only circular. We have in the radial direction a really high heat conductance. That's important. And as in the bitter approach, a high radial stress limit. We can adjust the current in there as it's a usual current excited magnet. And you can build really compact magnets out of that. And you might combine them. We will discuss that a bit in the next near future. But the cons are really due to the resistive joints in between these disks, there's no persistent mode available. And the heat load of the contacts, of these ohmic contacts, has to be cooled away. That's important. Are there other shapes for this Duda approaches? Yes, in principle, you can use not only circular disks, but in this case here, for example, rectangular ones, but the principle is the same of the stacking. And this has been already proven that it's quite successful to use that and in a master and in a PhD thesis. And then we had a student working on the optimization of the joints. And in principle, you can have large jointing areas for these rectangular ones outside of the original magnet area, so of the bore. And this means that you can really realize low resistance joints in there, having a large area so that you can live with that. So what magnetic field can be calculated by, can be generated by these type of Duda stacks? Here we need again Biot-Savart. In this, I cited that from a textbook in this case, and I do not want to go through each and every detail here, but this segment here, which is a leg of a Duda, might produce a magnetic field in this direction here. And if you consider all these legs of a Duda magnet, then you will end up with this presentation here. So the center magnetic field of a Duda stack is then given by this expression with length and width, number of sheets stacked on top of each other, and the current which you put in there. And this means that you can easily produce at 77K a small magnet which has a center field of about 4 Tesla. And this is well beyond what you can achieve with permanent magnets. By the way, just look at this expression here for the central magnetic field. and you see again that it's this relation. It's the third power of the distance to the point you would like to measure the magnetic field, and it's the magnetic moment in the top part of this fraction. So this gives you really a nice agreement with the previous with the previous calculations. And if you do that with some FEM calculations, so you can get the total image of a magnetic field of such an arrangement, which you can see here. So these are the stacks on top of each other, and in the center you can see again this can produce about 4 Tesla. And I said it's nice to have this rectangular dudas because in principle you can put them together in the shape of a so-called Halbach array, and this means in the top plane of so arranged stacks of rectangular tapes, you have an increase of the magnetic field, and here you have a weakening of the magnetic field. And with that, you see you can go even further with the same Duda arrangement than the 4 Tesla to 4.5 Tesla in the middle here in this area. So I would like to put some questions on you. It's perhaps not the most I will not answer these questions, but just you can make up your mind on that. So what do you think about the current profile in a Duda disk? How will be the current distribution over the radius? How about the quench behavior? Can you realize a Duda stack even in non-insulating technology? And a question, if you have some knowledge about low temperature superconductors, is it possible to realize this Duda approach with LTS? I can give you the answer, but you should think for yourself. And can you imagine which applications might be quite exciting for this Duda magnets or coils? We might discuss that at a certain opportunity. Okay, this was in principle very compact small stacking tapes to create novel architectures of magnets. And another approach is to use robotic windings to create new topologies of coils or new shapes. And this is a picture of our robotic winding cell at KIT ETEP. And you might ask, what is the motivation to go for non-planar coils? And if I show you the stellarator, a fusion magnetic confinement for a fusion power plant, you might hear more about that in the next lectures by Dr. Wolf. You see that these blue shapes are these coils which are required to shape the plasma in a stellarator. These are is a general performance data of that, but you see these blue coils, they look wild. And is this really a large number of individual coils, non-planar coils, which are required for that? Not really, fortunately. Here you see in principle, at least for some stellarator designs, you can live with only 5 different types of coils, of non-planar coils, and then you have some planar coils which are called A and B. But this is not a fully optimized setup. This is just one setup which is directed towards a minimum number of non-planar coils. And for this, it's really helpful to have this robotic winding, because you might see that there are some of these coils, for example, the number 3, which are a bit concave and have really complex shapes of the wire to follow. And therefore, we installed this robotic winding cell at KIT ETEP. And you see here, for example, this is a 6-axis robot, this 2. And here we have the positioner. So this is holding the former of the coil itself. And you need not only the robots usually have no hand. And to the right here, you see what we call a winding hand. And we will have the wire on the bottom of this winding hand, and we have there some possibilities to attach the arm of the robot and some controllers. And especially important is the rotary encoder, and there is some radial force sensor, which is important so that we can measure the winding tension during the process. And I can show you a movie we recently did on a non-planar winding. This is on the next slide here. And I hope I can start that. It's not so easy to do that in this presentation mode. Hopefully I will succeed. I have to find my mouse. Yeah. Here it's starting. So you see the positioner is rotating the former, and the robot is using this winding hand, and you see it's inclining a bit. It's not always horizontal. It's at the ends, it's going a little bit down. And if you look carefully at the long section of the coil, you see that it's a little bit curved. And we call that, this is a three-dimensional super ellipse. And you see the trajectory of the winding hand in the insert here. Oh, sorry, I have to switch to my pen again. Here you see the trajectory of the winding hand itself, how it has to move. And the complicated thing is really to model everything in 3D first, and then to check if it's working in the digital twin, and finally to realize that in the robotic winding. So in principle, as we have these 3 robots, we can really proceed with this robotic winding even for very complex shapes. With that, we leave in principle, the mathematics and this preparation of these windings, and go a little bit into the direction of cooling technology. So this is in principle a picture of a cold head, and what we are using that for high temperature superconductors is really to enable some, let's call it dry cooling. And how is it arranged schematically? First of all, usually you need a compressor, which then uses a gas to feed in and feed out the gas out of the cold head. It's a so-called Gifford-McMahon GM cooler. And what happens is that this copper cup here at the bottom is then the cold part of the cold head. And usually you attach something to this cold cup of the cold head, to this tip. And the most easy thing is to use a copper cold bus to cool our magnets, which is here, the magnetic windings, the magnet windings are here. And this means we would remove the heat out of the magnet by the means of thermal conductivity, by bulk massive conductivity. This is one option. And another option is to not use this copper cold bus, but to use a thermosiphon. And a thermosiphon has the advantage that in principle it uses the thermodynamic properties of the cryogen we are using in this thermosiphon. In this case, it's neon. Here it's liquid neon, and the return path is gaseous neon. And what we are doing here is usually we are condensing the neon here, then it drops down, goes down to the so-called evaporator, and as a gas returns then and is reliquefied here. The advantage is that we can use here the heat of evaporation to have an additional cooling effect on our coils. And a more detailed look on a simple setup is shown on the next slide here. So in principle, we have a vacuum cryostat, green, we have the MLI just to have an irradiation shield. We have the cryocooler or the cold plate, this tip, this finger. We have a gas reservoir at the outside. We need that, it's clear. You have to know what pressure is in the system. Then you have some heaters at top and bottom because you have to assure that the overall system always is at a temperature higher than the triple point of your cryo media. Otherwise, your media will freeze out. Then you have some temperature sensors for the top and bottom part of this thermosiphon. And as I already indicated, we have a flow of liquid and a flow of gas up. This looks a little bit complicated. So what's really the benefit of you having such a device? The benefit is if you compare that with a copper cold bus, so here to the left we have the copper cold bus, then we can transfer for in a given cross section roughly 7.2 watts of heat from the warm end to the cold end. Whereas if you have the same diameter with a thermosiphon, you can transport more than 100 watts here. In principle, if you stay within the limits of the system or of the design limits, then you can transfer the maximum power of the cold head in a tiny cross section. This is really an advantage, and it's more flexible. So in principle, the copper is rigid to have a good thermal conductivity, but the thermosiphon can be really hollow tubing of thin wall thickness and very flexible shape. And you can even do that with flexible hoses. But where to get all these cryogenic data from? Just a hint to yourself. There is a library available in a lot of different interfaces. Here, for example, I gave a Python code segment if you want to you get some information on Neon in this case. And here you have all the links for all the different software packages or modeling packages you would like to have. And there you can really get all these values out of for free. This is public domain, open source. Okay. Away from the thermosiphon, back to the cold head. Now we want to use our cold head at a certain temperature, and now we assume that we would like to use the operating temperature of 30 K. This means 30 K is here, so we would expect, according to the capacity curve of the company, of the supplier, of roughly 130 watts at 30 Kelvin. And what you can do is you use the capacity curve, so watts versus temperature from the supplier, and do a linearization with that. And this leads either this formula here, or which is more appropriate for us, you can linearize these cold head around the temperature of 30 K by this formula. So the temperature is depending on the heat load, and this is the appropriate relation to that. And by this, you can try to build a thermal equivalent circuit for this cold head. And this is shown on the next slide here. So in principle, we have here the absolute zero temperature as ground. Then we have a temperature source. This is exactly this 8.5 Kelvin out of the linearization we had. And then we have here our, let's say, internal resistance of our temperature source. And this means then we have the full capacity here. And as an example, there is a heat load of 130 watts given for that. And you can easily model that in a software package, LT-SPICE, you perhaps know from your studies in electrical engineering. So here is a download link for that. And with that, you can really model this, and we will do that later on. To study how these can be support when you are considering, for example, magnets, we can use an example magnet. And for this, I prepared this sketch here. So we will have our cold head on the top. Then we have a vacuum vessel in here. A persistent current switch might be used for the superconducting magnet. In this case, it's just considered. We have here the cold part of the cold head. And in this case, we have not a thermosiphon, but we have a copper cold bus here to the magnet itself. Here we have the persistent current switch for the magnet itself. We have current leads which have to feed the current into the magnet, at least, or from the persistent current switch to have a shortcut. We have the magnet itself, and in the middle we have the free bore. And in this setup, we have several heat loads which are already included here. And I do not want to go into details in the discussion of that, but just to provide a table of the heat loads we would have to compensate. The most important heat load usually in magnets is the current leads, because they are usually optimized for current, and this is really quite high. Then there might be the persistent current switch, because this has to be heated, but this is not steadily. This is just during switching processes, this heat load. Then we have something which is can never avoided. This is a radiant heat, and this will be a constant heat load on the system itself. The coil itself might produce some heat if you have some joints in here, so there will be a maximum value of that, and there might be a maximum value for the ramping loss, because each and every superconductor creates some loss during ramping. So these are the main 5 heat loads we have to consider. And these have to be integrated into the thermal equivalent circuit. And this is shown on the next slide. And you see more details here. And we'll switch to the LT-SPICE program in a second, because then you see what the advantage is of that. But in the bottom part here, you see again, we have in principle, we have our cold head, and then we have, in addition here, because this is just the location where the heat from the persistent current switch will come, and the heat of the current leads will directly enter into the cold head itself. And we have these heaters in here, which I mentioned already in the discussion of the thermosiphon. You have to control the temperature. You have always to have a reserve cooling power or a heater in there just to have constant temperature. And what's important is that you make yourself aware that the voltage in the electric circuits is now becoming a temperature, or has to be interpreted as a temperature in a thermal equivalent circuit. The current has to be interpreted as a heat flow, and the electrical resistance now becomes a thermal resistance in this case. So, and for that, now we have to switch to the to LT-SPICE, and I will show you what is really the big advantage in there. I hope I can do that immediately. Here it is. So this is exactly the same as you saw in the PowerPoint presentation. And the good news is that now you can run this LT-SPICE program, and then you see that we have to the right the circuit as it is not changed. And for example, here at this position, there would be, or there is at least the magnet itself, so the currents and coils of the magnet. And we can easily check what temperature is there by using the tip, the measurement tip, and putting here. And you see in this case, we have a temperature of 21 volts, but remember, this means Kelvin. This means, in principle, this is below our operating temperature, and we could, for example, reduce the reserve heating power, and let's just put it to 0. And then the temperature should decrease a bit. So, and let's run it again. And you see, yeah, it's now about slightly more than 18 Kelvin. So in principle, if we really want to go for the operating temperature of 30 Kelvin, then we have to put much more power in here. Let's assume what happens when we go for 50 watts in here. And now, now we are approaching 27 Kelvin, so we would still need some more. Remember, the full power load, power capacity of the cold head is nearly 130 30 watts. And now you see we are approaching this 30 Kelvin, so you can easily see what happens in there. And the advantage is, without any FEM or any calculation, you can easily check what happens, for example, if the PCS is producing more heat load, more heat flow into the system, or if your insulation has a breakdown. So, for example, here, let's assume that we have 10 times more heat in here for the radiant heat. What happens then to the temperature? Not much in this case, as this is less than a watt. So, but we can even check if this value is increasing, if we are still increasing that. Let's assume that now we get 4 watts in. Yeah, and now you see that the temperature is increasing. And you can check that easily without any FEM, and you can introduce some thermal contact resistances, some additional kappa parts or whatsoever. So this is really a nice thing what you can do here, and much more in there. So, for example, for more complex things like rotating machines, it becomes much more complicated, and this is a big help because you can easily do that without the time-consuming FEM calculations. So, is this for real? Was this really a help? Yes, it was, because this magnet was definitely built, and you can see that on this slide here. This is very similar system to what we discussed as a magnet. In this case, this would be the open bore, and it's a cryogen-free cooled magnet with the heat loads just with the thermal equivalent circuit we just discussed. So, what have been the learning objectives in this intermediate lecture? Let's call it that. So first, you have seen the selected basics and challenges in magnets and magnet technology. You should have at the top of your head the magic triple, which allows you to calculate and design magnets right on the back of an envelope. We elaborated a little bit on the recent developments in coil and winding technology using the second generation of high temperature superconductors, for example, the Ni coils, the Duda coils. We discussed on how to use a cold head in a magnet by conduction cooling or a thermosiphon. We introduced this analogy of thermal equivalent circuits to the electrical equivalent circuits, and we used a little bit this LT Spice. I can strongly recommend that. How to linearize the behavior of a cold head was shown. We just listed the heat loads of a magnet in here, and not only I mentioned that, but we tried to see what is happening when we use backup heating power, what's happening to the to the magnet and the temperature of the coil itself. So in case of questions, please direct yourself to the other lecturers or write me an email with your question, and we might try to follow up on that afterwards. So thank you for your attention, and have a fun with the remaining lectures of this lecture series.